So today we will discuss persistent homology, but a couple of comments first. I finally remembered to turn on everybody's mic so you can ask questions either via chat or with your mic. Just turn on your mic and you'll be able to ask without raising your hand, but you're welcome to raise the hand as well. So either way works. I'm using a different tablet today, but it's not a newer one yet. If any of you recommend a good tablet, let me know. I will try to get one this week, and hopefully we won't freeze up today and need to switch computers. So today we will discuss persistent homology as well as next time, and then on Monday we will discuss the JavaPlex software for computing persistent homology. So just to remind us, we want to go ahead and count holes. Our holes might have to actually, well, our holes could be holes like this. They could also be, so we might have this two-dimensional hole right here. We could also have higher dimensional holes, so a sphere contains a three-dimensional hole, so we can have lots of different types of holes. We want to count them, but we want to count them as we grow our complex. And so we want to note that in this particular case, we have 1, 2, 3 holes. So our Betty1, which counts our number of cycles, these kinds of things, is 3. So we've got these 3 holes right here. When we increase our radius, 2 of the holes get filled in, but another hole gets created. So we now have 2 holes. So our Betty1 is 2, so we went from 3 to 2. But we didn't just go from 3 to 2. We went from 3, we lost 2, but we gained 1. So we want to note that as well. It's useful to know how long your hole lasts. So in this case, our 2 small holes did not last very long. So we wanted to note that they did both go away very quickly, even though we noticed that a new one was created. So we will go over how to calculate that today using 2 different methods. But first, a few definitions. The 2 papers that we will be discussing today is computing persistent homology. That is the main way that we will compute homology. It gives us the most flexibility. It uses matrices. But we will also discuss another paper called, So it was a different tablet, but unfortunately not a tablet that works. So we're going to switch to another one. So the computing persistent homology was published in 2005. The originally persistent homology was defined in 2002 in relationship to data analysis. There were other papers that came out at similar times. You can see my website for links to those papers. But the original one gives a very pictorial description, so it's nice to have a pictorial way of looking at these things. I think we have a 4th computer to try on Friday. If that doesn't work, I will continue to use my Mac, even though my handwriting on the Mac isn't very good. So the 2002 paper is this one, and gives us a nice visual description of the homology. So we will discuss both methods, but first we want to go over just some definitions. One of the things that we mentioned last time is we are growing, our complex. So in this particular example, in this vision paper, they started off with 50 data points. So this was just 50 random data points that were generated around the surface of a torus with a bit of noise, just to see if they could reconstruct this torus. So we start off with 50 bars representing the 50 zero-dimensional homology components. So you've got 50 vertices, 50 components, and so there's 50 bars right here. And they last for quite some time until we grow our epsilon balls and we start connecting vertices. We start connecting some vertices, and we can see when that happens at this particular time here. We reduce the number of components. That's about it. Our first dimensional homology, we don't have any cycles yet. Over here, as we increase, we will eventually get cycles, but right now we don't have any cycles. That's represented by over here. This is the actual thing where we've got 50 vertices. The blue means that no triangles have been created. So this is a subset of this. So this complex here is contained. We still have the 50 points. We just now have edges between them. As we continue moving in time, growing our epsilon balls, we can now take a look at this time bit stamp where we now only have one component. So our Betty naught is 1. So we just have the one component. We start now having a bunch of cycles. So now that's easier to see in this picture where the red represent faces that have been formed, so the space has been formed. The blue represents we have not filled this thing in yet, and so we do have a cycle. And so we can see that we have, depending upon the various times, we have different cycles that form. And then, so this is contained within this complex here. We're supposed to actually have filled in, so most of these things are actually filled in as illustrated over here. And continuing on, if we get to this stage right here, you can see that most of these things have been filled in. We don't see the blue, but if you see the animation, you'll see that there's still a few blue things where we have not filled in, and so we still have a few cycles left, as well as filling in this two-dimensional thing. Oh, sorry, I'm wrong. All the triangles have been filled in at this stage. So at this time, all the triangles have been filled in. But we now know that our Betty numbers, Betty naught is we've got one component, so we can see one bar here if you have really good eyesight. So that's our Betty naught. Our Betty 1, we have 2 cycles. So we have 2 cycles. So we have 2 cycles, the longitude as well as the meridian. And so that will persist. So these two things persist for a while. And then we also now have a 2 cycle, which is the inside of this donut. So if you've eaten all the cake and just left the frosting, we've got the inside of this donut. But what we want to focus on today is that this embeds inside of this, which embeds inside of that. Any questions so far? Having all of this nice embeddings means that we have a filtered complex. So with this filtered complex, it just means we have a bunch of simplicial complexes, each of which lives inside of the next one. So we can start off with exactly 2 vertices. When they enter in, they're sort of a lighter color. And so now at stage 1, we will create 2 vertices. At stage 0, so that was at stage 0. At stage 1, we will add in 2 more vertices, plus add 2 more edges. So note that a filtered complex is actually more general than this point cloud data that we've been growing. So a filtered complex is used in a variety of settings. Sometimes we're interested in data where we're looking at distance. Sometimes we might be having a Morse function where we might be growing our function using a Morse function instead. We'll talk about various applications later, but we want to talk about the most general stuff where all we have is this increasing sequence. It might be finite, so in this case we have exactly 6 simplicial complexes, but in each case they live inside of each other. And the dotted just means that we created this edge AC at time 3. The lighter colored, it was created at time 4. The darker colored meant it was created previously, but we now created this thing at time 5. So we can use, though, that, notice that we've got double subscripts. So our superscript, we can think about that as time. In our data, it could have been our epsilon radius, but so our superscripts will be time. We still have our standard subscripts. Our subscripts had to do with our dimension. So our subscripts, this is our dimension. So we have 0 simplices in this case. We can have our 0 simplices. So if I take A and B, these vertices, they are 0 simplices, but they exist at time 0, at time 1, at time 2. So my 0 simplices, A and B, are in all the complexes, even if I restrict to, dimension, when I restrict to dimension 0. If I talk about my 2 simplex, so this is my A, B, C, this is my 2 simplex, it is 2-dimensional, so it is in C sub 2, but it exists at time 4 and time 5, so we've got it in both of those complexes. So we will use double scripting, super and subscripts, to denote time and dimension respectively. We will also use a bit of shorthand. Instead of using the set A, B, C to denote the unordered triple, we will just say A, B, C instead for shorthand. And so this represents the set containing A, B, C, or the 2 simplex created by the triangle A, B, C. And similarly with edges, we could have used the set notation here, but for shorthand, we will just use AC to represent the edge AC, or CD to represent the edge CD. We could talk about our homology, talking about kernels mod images, or null space mod column space. We also used, but not that much, cycles mod boundaries, and that's what the notation we'll mostly be using. So when I say the term cycle, that means that I'm talking about the kernel of a boundary map. It also means I'm talking about a generator. So a cycle is a generator of our homology. It is in the kernel of our boundary map, and that was our generators. Versus if I say boundary, then I mean the image of a boundary map, and that also had to do with our relators. We modded out by our boundaries. And so our cycles are our generators. Those are the things in the kernel of a boundary map. And then the boundary is our relators. Those are in the image of the boundary map above. We will, in today's lecture, instead of drawing this thing horizontally, we will switch to vertically. So now our boundary maps, we will go from our 2-dimensional space, we will go from our 2-dimensional space to our 1-dimensional space via a boundary map, or from 1 to 0, or from 0, the 0-dimensional vertices, sending everything to 0. And then we can take any triples, for example, C1, C0, and 0, take any of these triples, and calculate homology. We will just write it vertically instead. Do note that since in this last map right here, all our vertices go to 0, that means all our vertices, every single last vertex, is a cycle. So all vertices are cycles. They're all in the kernel. So our vertices do correspond to cycles. So now, because we have our dimension, so I've got the dimension right here where I've got my boundary map, so that corresponds to my dimension, which we're drawing vertically now. But I also had my filtration. So if I think about this thing in terms of time, or whatever you want to use for your filter, You might use a Morse function, you might use density increasing or decreasing. You might use epsilon balls. I'll use the term time, but it can again be anything. But we now have this two-dimensional collection of maps here, where in one dimension, in the vertical dimension, we're referring to the boundary map, and so I can talk about the homology in my vertical dimension, since that's the boundary map, so we can do our homology here. But I also have my filtration, so I also have my horizontal filtration, where at time 0, I was embedded into time 1, embedded into time 2, and so we also had our filtration in the horizontal direction. So we can see in terms of our filtration, I've got, in terms of my filtration, if I'm at time 0, then I can talk about my homology at time 0. I can also talk about my homology at time 1. I can also talk about my homology at time 2, etc. So they just depend upon the different complexes, but each of these complexes are embedded. So we have this inclusion map where at time 0 we include into the time 1. At time 1 we include into time 2. We can actually be more general than this. I am assuming the inclusion map for these things, but they don't actually need to be the inclusion map. So as long as we have some map that sends our C00 into our C01 or our C0 into our C1 for all dimensions, any map will do. It does not have to be the inclusion map, but normally we will work with the inclusion map. So we talked about we want to do our homology. So again, I can do my homology at time 0, my homology at time 1, our homology at time 2. But I do need to distinguish between these. I don't want to use H0 for these various different homologies, because after all, at time 0, what is my H0? Well, at time 0, my H0 is going to be 2, because I've got 2 connected components. At time 1, it's still 2, but that's because I've got these 2 different connected components, versus at time 2, I only have 1 connected component, and so my H0 is 1 at time 2. And so since we're using superscript to denote time, we will use superscript here as well. And so we've got our HI business here. That just tells us what homology at the various times. So H0 at time 0, if I is 0, is 2. H0 at time 2, when I is 2, would be 1. You will notice, however, that I added this little comma 0. Well, it wasn't me, it was Zamorodian and et al. Who added this, because we can talk about how long things persist. And so what we're really going to be talking about is, for example, my H0, 1, I will take a look at cycles created at time 0, but I will mod out by, do they last 1 unit later? So do they last 1 unit later? So if I talk about H of 0, 1, the 0 business right here tells me that I'm looking at these cycles. So I'm looking at the cycles created at time 0, so I'm looking at the cycles created at time 0. But what I mod out by is not the boundaries at time 0. I'm going to mod out by the boundaries at time 0 plus 1. So I'm going to go over 1. And so I will mod out by these boundaries. So if we take a look at that, my cycles are A and B, but now I will mod out by the boundaries. The boundaries I have at time 1 are AB and BC. Well, modding out by the boundary BC, that gives me C and B, but I don't care because C doesn't exist at time 0, so I want to restrict to the cycles. I want to restrict to only the cycles at time 0. So that's why we intersect. When we mod out, we have to intersect by only the cycles at time 0. So yeah, it looks like I'm trying to say that we've got A and B. That's our cycles at time 0. Then my boundaries are, I do have that A plus B equals to 0. I also have B plus C equals to 0, but I don't care that C equals to B because I intersected it with, just my cycles at time 0. So I only had an A and B. I don't have a C. And thus, we now get that this thing right here, that if I take a look at the actual maybe not how many Z mod 2s do I have, how many components do I have? Well, I only have one because I have the two things that were created at time 0, but at time 1, I got rid of one of them. My edge here, I can remove either A or B, and so I just have the one component when I'm only interested in the component containing only the cycles A and B. So that's one way of taking a look at persistent homology. We will frequently use a more visual representation where we'll look at persistent at various different times. But this is, we can now talk about pairs of things. So we now have a pair of cycles created at time 0, but destroyed 1 unit later. We can also take a look at cycles created at time 0, but destroyed 2 units later. In that case, I take a look at my cycles created at time 0, so that's my null space again. And then I take a look at what is destroyed 2 units later. And so in this case, I'm now looking at these things. So I've got my cycles A and B, but I mod out by my edge AB again. And so I still get that my theta not the number of components of 0, 2 is still equal to 1. And thus my H0 superscript 0, 2 is just one copy of Z mod 2, because I'm assuming we're using Z mod 2 coefficients. So any questions? We can do this for any time I, and so, no matter what my, I is, maybe my I is 1, and I do it by 1, or maybe I take my I being 1, but I go off 2. We can do lots of these things where we just choose that we've started at some I, so this is where our cycles are. So we will start off at, say, some I. In this case, I let I equal to 2. And then we look at the boundary P units later. So P units later, we mod out by that boundary. So we might be doing this, and, well, 2 units later, or 3, maybe I do 3 units later. So if my P is 3, I could be modding out by that. And I can, again, do any dimension whatsoever, whether I'm doing my 0-dimensional simplices, my vertices, my cycles, 1-dimensional cycles, whatever I want to do. We can calculate this. So we now have lots and lots of different homology that we can take a look at. So let's take a look at calculating that. So remember, again, we're going to take a look at cycles, mod boundary. So we want to take a look at cycles, mod boundary, and we want to compute this homology. How do we compute this homology? Well, first, just to emphasize, we'll be using the term cycle a lot. So if it's in the kernel, it will be a cycle. So if its boundary is 0, it will be a cycle. So in other words, all vertices, so if I've just got a vertex, that's a cycle. This sort of thing is a cycle. this right here would also be a cycle. We will then mod out by boundaries. And so if I have this thing here and I fill it in, well, then the boundary of this two-dimensional thing, I'll go ahead and mod out by the boundary. The boundary of this two-dimensional surface is this one-dimensional cycle, and we will mod out by that. Now, in terms of, so again, we're going to start off now by discussing the 2002 paper. This gives us a very nice visual description, but we will later use matrices to talk about a more efficient, more robust, we can do more with it using matrices in the 2005 paper. But having a nice visual representation is nice, and a lot of papers will talk about positive and negative simplices, so it's good to know what they are. The picture, however, I took the simpler example from, so this picture is actually from the computing paper, so we're going to start off with a simpler example, but we will look at a more complicated example later from this paper. So definition, we've got a positive simplex is if it creates a cycle when it enters. So in other words, it's going to be, we're going to choose that to be our generators. A negative simplex will be something that destroys a cycle when it enters. And so it will create a generator. So it will create a generator. So if we look at things that are positive, well, things that are positive are vertices will always be these cycles. And so all our vertices, so all these vertices, they are all positive. So all our vertices will be positive. We then have at this stage here, we just destroyed a zero-dimensional cycle because now we've joined these two vertices into a single component. So we can think about this as destroying a cycle. So this edge right here changed that we used to have two cycles, but now these cycles, if we mod out by the boundary, we can destroy one of those cycles when we mod out by the boundary. And so it is a negative simplex because it's a destroyer. It destroyed one of our generators. So we had two generators, A and B, but we added this relator, which destroyed it, and so it is a negative simplex. So a positive simplex is something that creates a cycle. It is a creator. A negative simplex is something that destroys a cycle. It is a destroyer. It also corresponds to a destroys a relator, not a generator. It creates a relator. It creates a relator, and thus when you mod out, you destroy something. Versus a positive simplex creates a cycle. It creates a generator. So if I take a look at step 2, one of these two, let's say this one, destroys an element of H0. So we added, so going from this step to this step, we went from 3 components we went from 3 components, these 3 components here, down to, now we went from 2 components, so this one component and this component, now down to just 1 component when we add this edge. So we can say CD is a destroyer, but then when we add in AD, it will now create a cycle, and so AD will be a creator. It will be a positive simplex. Notice that in this particular example, since we have multiple things entering at the same time, I had to make a choice, and I chose CD to be the destroyer, and I chose AD to be the creator. Somebody else could have come up and done it differently, and that would have been fine. We would have gotten the same homology at the end, but our generators and relators would have been a little bit different. So a choice does get made when you enter in too many simplices at a single time. So now let's go ahead and mark which ones are positive. So we have all of these because they are vertices. All vertices are positive. And you will notice that I've decided that AB comes before BC, comes before CD, comes before AD. So we've sort of ordered these things. And so this was the time I was supposed to have been working with. But because multiple things entered at the same time, I'm going to, for now, work with this time. So we will temporarily ignore the time we were supposed to be working with. And now we're going to work with this artificially created time where I arbitrarily chose, well, actually, Zamarodian and Carlson arbitrarily chose AB to enter before BC. And so we now have that, well, AB destroyed a component, BC destroyed another component, so these are both negative. CD came in, destroyed another component, so that's also negative. But now when I add in AD, I create a cycle, so that will be positive. Note I only have two choices in terms of this homology. I'm either going to be destroying something in the preceding dimension. So by adding this edge, I destroyed my zero-dimensional, my H0 number of components. Versus when I add in this edge, I now created a one-dimensional cycle. So I now create a one-dimensional cycle. So an edge will either create a one-dimensional cycle or it will remove a component. So it will remove a zero-dimensional generator. We can then add in AC. With AC, we have now gone from one cycle to two cycles. And so AC would be positive. With ABC, we now have our ABC now is a boundary. ABC being a boundary, we can now mod out. So we had this cycle ABC, but it's a boundary, so we can mod out by it. So we've just destroyed the cycle. And then when we add in this triangle here as well, we've destroyed another cycle. And so now we know which ones are positive and which ones are negative. To determine which ones are positive or negative, I like matrices, but there's also a number of graph theory algorithms that will determine whether or not you created a cycle. The next thing that we want to do is pair our cycles with our boundaries that are destroying them. So I'm going to take a look at all my negative ones. So I'll take a look at all my negative ones, and I'm going to pair them with something, with one of its elements of its boundary that we will say we're going to mod out by that one. So AB has boundary A and B, so I could destroy either A or destroy either B. The computer needs us to make a firm decision, and our firm decision is we're going to kill the youngest. So if you're the youngest, I'm sorry, you're going to get destroyed. So 4 will get paired with 1 because we are going to use 4 to destroy the youngest one. We're going to use 4 to destroy B. So AB will destroy B, so 4 gets paired with 1. BC, when the youngest here is C, so 5 gets paired with 2. If it had been previously destroyed, we will have to go backwards. We will look at that with a different example. So if I had ordered these things differently, we might have already destroyed B, in which case we cannot destroy B again, but we'll see a different example for that. CD, it destroys either C or D. D is the youngest, so we will do that pair right there. We now look at our next negative ones. Our next negative ones are ABC. The boundary of ABC is AB, BC, and AC. Well, which ones are the youngest? Well, AC is the youngest, so 9 will be paired with 8. And then we also had this destroyed something. Well, so we paired, notice we paired, so 9 was paired with 8, so my triangle ABC was paired with AC. We now need to do ACD. Well, its boundary is this, which also includes AC, but we've already destroyed AC, so we're going to have to go backwards and kill the next youngest, and the next youngest, AD, is part of the boundary, so we will pair it with this one right here, and so we have our pairing. So that can tell us now how to create our homology, because we know what our generators are, and we know what relators are destroying them, and we know which generator it's destroying. We've just chosen which generator it will destroy. So any questions up through here? There is another row in terms of this going backwards when we have to skip that can actually get a little bit more interesting, but we will use a different example to illustrate that. So I'll just show you the last row. The last row is basically all the positive simplices in its boundary that are fine for it. The fine for it will show in the next example. For here, this is a simple example, so I just list AB, I just list BC, etc. For here, I only list AC because if I take a look at AB, AB was negative. I only need to kill generators. AB is not a generator, so I'm only listing generators here. So that's why AB is not listed. That's why BC is also not listed. And so that's one of the rules in terms of listing, is you're only listing the generators, so you're only listing the positive simplices. But there is another rule in addition to that, which we also will take a look at soon. Any questions up through here? So to take a look more at this example, I can now use this thing here. Yeah, it was nice to have the picture associated to it, but I don't need the picture anymore. The homology is completely contained within this table right here. And there's a nice graphical way of representing that. And the graphical way of representing it is to use these triangles. So we will go back to time 0 soon, but I'm going to start off with time 1 first. At time 1, we create a cycle. And so anytime we create, we're going to get this vertical bar here. So I created a cycle at time 2 with C, create a 0-dimensional cycle at time 3 with D. I created a 1-dimensional cycle at time 7 with AD, created a 1-dimensional cycle at time 8 with AC. Again, we're ignoring these times up here. We will get to them later. Right now, these are the times we're going to be dealing with. We can see also that at time 4, we destroyed B. So we use this dashed line here. It's going to give us more information than you might expect. If I draw this dashed line with slope 1, we'll explain the slope later, to connect AB to B0, to say that it was connected here. So AB destroyed B, it was paired, these things were paired, and so since these things were paired, we draw this dotted line connecting these things here. BC was paired with C, so I will draw this dotted line. So note that in order to create these collection of triangles, I just took my simplices in the order that we put them in, and I put them right here. I put them on my x-axis, so my x-axis is each of the simplices as I'm growing them. And then we just go ahead and if this thing creates something, we then connect it with a line of slope 1 to whatever it destroyed. So since it was destroyed by 6, we go at time 6 to destroy it. Here our AD was destroyed at time 10 by ACD, so we connect it with this triangle. AC was destroyed at time 9 by this triangle, so we connect it, and so we have lots of nice triangles. So now we've got the triangle, so that's one picture. This is the picture that we generally like. These intervals right here. So that's the sort of thing that we like. We like those intervals. And notice I can get those intervals. Oh, I forgot one thing, so let me go back to this one right here. Remember I said I would go back to time 0. Time 0, we did create a simplex. It never got destroyed, so it also creates a triangle, but the triangle it creates is the infinite triangle. So there's another triangle here as well, but it covers everything. And so we also do have a triangle that was created by A0, and since it never got destroyed, we have this infinite triangle here. So on this next page, we do have this infinite triangle where we start off with A0 and it goes off forever. And notice I can now see my barcode. So we like this thing right here. This is our barcode. That's B-A-R-C-O-D, in case you can't read my handwriting. B0 started here and ended here. So note, I can use the base of my triangle. I can use this base of my triangle, and that becomes my barcode. And so I'll just move this thing up, and that's part of my barcode. C started here, the triangle ended here, so that corresponds to this part of my barcode as well. Similarly with D starting here, ending here, we've got that part of the barcode. Our AD starts here, ends here, and so we've got this part for our one-dimensional cycles and killing our one-dimensional cycles, and our last triangle starts here, ends there, and so we've got the last thing of our stuff. So what this tells us is it tells us when our cycles are created and destroyed. So if I take a look, actually, let's go back to our picture. I should have included one with the picture. It tells me when my cycles are created or destroyed. So if you keep that picture in mind, then we can think about our cycles being created and destroyed at various different times. We can also figure out now what my Betty not say of, say, 0, 3 is. Betty not of 0, 3 means I take a look at my cycles. So these are my cycles that have been created, and I look at what was destroyed 3 units later. So I look at what's destroyed 3 units later. Well, it still exists 3 units later, and so I still have my one cycle. It didn't get destroyed. Versus if I take a look at Betty not of 1, 3, then I can take a look at my cycles that were created at time 1. Take a look at what was created at time 1, but then what gets removed 3 units later. Well, that's why we have an open interval here, is because we've destroyed B when we added in AB. So we start off with AB. So we start off with our 2 cycles. That's why it's a closed interval right here, because we've got the point A and the point B, but then we mod out by AB. And so I can see that if I look at just these 2 bars, and if I look at a vertical line crossing through these, it only intersects them once, these 2 bars, and so my Betty not is 1. And so if I take a look at a bar, if I take a look at now Betty 1 of, this is 1, 2, 3, 4, 5, 6, 7. So 7. So Betty not of this, and then maybe I'll do 7, 1. Then I want to know what cycles came in at this time and still exist. So I want my line to just go through this first line. And so you can calculate these persistence indexes using your barcode. You can also use it during the triangles, and we'll show that in a later example. Okay. But in reality, these things, A and B, actually both entered in at time 0. Oops, sorry. Okay. Oh, I went a little bit too high with my mouse. Let's try not to do that. These all entered in at time 1. These both entered in at time 2, and this was 3, 4, and 5. Oh, you're not seeing it anymore, are you? I think everybody's seeing things now. So good. So hopefully that didn't last for too long. So now we've got these entered in at time 0. These entered in at time 1, entered in at time 2, 3, 4, and 5. So basically, the computer needed each individual simplex to enter in one at a time. By the way, with matrices, you don't have to worry so much about this. You still have to order them, so there is definitely still an order with matrices too. But yeah, there's still an order with matrices, but the way to calculate this thing will be a bit easier. But now I want to, in order to do the time, there'll be another way to represent the time, which will make it very easy. We can work with a single matrix rather than lots of matrices for each dimension, for each boundary map. So now I want to collapse all of these to time 0. So that's what I do, is we collapse all of them. So at time 0, I have both A. So A, remember, was my infinite triangle. So I still have this infinite triangle, so that still exists. Plus, I take this triangle here, and I move that edge over so that it now starts at time 1. For my time 1, I now want to note that this thing entered in at time 1. So when I am squishing this triangle and moving this triangle, the one edge got moved over to time 0, but my hypotenuse here, it's now going to end at time 1. And so now I will get a barcode for my B0 that goes from time 0 to time 1. We do similar things with C1. It's already at time 1, so it's at time 1. Oh, but then it gets destroyed at time 1, so it disappears altogether. It would be a dotted line, because if I squish this particular triangle right here, it gets destroyed at time 1 at the same time it's created, so we won't even see that in this at all. My D, though, did enter in at time 1, so this actually corresponds to D right here. So this will actually correspond to D. And that triangle here will get squished to ending at time 2, and so it will end at time 2. So we've now squished 4 triangles. Our infinite triangle here, so the infinite triangle starting with A0, that's still an infinite triangle, so we actually didn't have to do anything with it. Then we had this triangle here. So that triangle here became this triangle. The triangle right there got squished all together, so it disappeared. This triangle right here became this triangle right there. We now want to squish 2 more triangles, except for they don't need any squishing because they came in at times 2, 3, 4, and 5. So we can just put them back in at 2, 3, 4, and 5. So even if your computer program has to generate something that's a little bit more complicated, we can go ahead and squish it into this format here instead. So any questions about that? So we will take a look at a more complicated example very briefly at the beginning of class next time, and then we will talk about using matrices, just so you can see your matrices. We will keep track of time within the matrix. So we will be able to take a look at all the superscripts at once in terms of our boundary 1 map and boundary 2 map similarly. So we'll do that on Friday. Any questions? So see you on Friday.